Hi, everybody. Welcome. Thank you for joining us today. My name is Jennifer McConnell, and I'm the product manager for the In Situ systems here at Protochips. Today, we're really excited to show you the first commercially available system for electron beam induced current analysis, or EBIC, in the TEM. And in the combination of EBIC and TEM, it's also known as STEBIC. And this is through a joint solution from Protochips and Point Electronic GmbH. So you will be hearing presentations from both companies today. From Protochips, we have Dr. Rémy Berthier presenting. Rémy's particular expertise is in situ electrical characterization of devices in the TEM. And he spent his time during his PhD at CEA Grenoble working really hard, especially on sample preparation for these types of experiments. While he was there, he actually collaborated with Protochips to develop an FIB optimized sample support that has since become actually our most successful commercial offering for in situ electrical characterization. And you'll hear him talk more about this sample support in his talk today. From Point Electronic, we have Dr. Greg Moldovan, and he's their Chief Technology Officer. Point Electronic is a supplier of electronics and software for electron microscopy. He manages particularly technology, development, and marketing. And Greg has previously worked for Oxford Instruments Nanoanalysis, University of Oxford, and University of Cambridge. Greg holds a PhD from the University of Nottingham, and his diploma is in physics. So real quickly before we start, if you have any questions during the presentation, please enter them into the chat box on your screen, and we should have some time at the end to answer a handful of them or so. Any questions that don't get answered, we'll ensure to reach out to you individually and get you a response. Also, if you experience any freezing of your screen or loss of audio in the middle of the presentation, we found that quickly signing out and then signing back into the presentation refreshes the screen and gets things going again for you quickly. It's a little inconvenient, but you can do it pretty quickly, and we've had a few people that have experienced freezing in the past. Okay, so without further ado, you didn't come here for me. I'm going to hand it over to Rémy to get us started today. Rémy, let me change the presenter to you. And all right, sir, you have the screen.
Well, good. Thank you, Jen, for the introduction. Before we get started and we address the core topic of today, both myself and Greg would like to tell you a bit more about both company, Point Electronic and Protochips, and where we're located in the world and what our activities are. So Protochips headquarters are located in Morrisville in North Carolina, United States. This is where all of our software and hardware work is being done, from design to manufacturing and final testing of every system. We have also sales, application, and service activities for the US located there. And for since 2018, for the different region, we have offices in Germany, Japan, and China, which are specifically dedicated to sales, service, and application support to be able to reach locally our customers more efficiently. And finally, I want to emphasize on a very important relationship that has been built since the very early days of Protochips with both GOL and Thermo Fisher Scientific. And this collaboration has been extremely important in the development of our in situ solution, and it's been particularly important for our latest development in terms of machine vision software platform for transmission electron microscopy. So you've probably known us for our in situ market and our in situ solutions, but initially Protochips is actually a MEMS design and fabrication house, and it's very early on in the days of Protochips when we were located still at the North Carolina State University that our founders, our CEO, our founders, they identified that MEMS chip and those devices could bring major advantages in the field of transmission electron microscopy in order to enable in situ experimentation. And this is where our different products were developed. This is where our main activities were defined. And we have so the Fusion Select system for heating and electrical characterization in the TEM, which is going to be what we're going to talk about today. There is also the liquid cell holder, the Poseidon Select for electrochemistry and liquid heating. And finally, the gas cell and gas heating system for TEM, the atmosphere. And more recently, and it's going to be an important part of our future at Protochips, we developed this machine vision software platform for TEM called Axon, which I'm going to tell you a bit more later. So I'm going to now pass it to Greg for Point Electronic.
Hi, everyone. Point Electronics, it's a small independent company in Germany. We're based in a small city in Halle on River Saale. We are suppliers of electronics and software for microscopy. We've been in business for 30 years. So we have quite a long running experience in dealing with all kinds of components for microscopes. We do not supply microscopes ourselves. We do not make lenses. We are primarily scientists and we have a very strong base in engineering. Our product portfolio is split in maybe 4 equal parts. We deal a lot with custom, one-of-a-kind or low-volume sets of electronics, complete sets of electronics for microscopes. For example, we deal with things like deflection system for quadrupole and octupole, special electronics for special ion sources. And we also deal with more than just electron microscopy. We also deal, for example, with optical microscopy, so we deal with laser scanning. But today I want to speak for another branch of our product range, and that is what we could call system or add-on systems, things that you add to running microscopes, whether they're new or been running for a while. And in there we deal with systems for electrical analysis, and I will cover that in detail today. But we also deal with other kinds of add-on systems, things for geometrical analysis, so things like 3D scanning at micro and nano scale, also surface topography and other such techniques. And lately we were involved more and more in kind of in situ environmental microscopy, which is a very exciting area for me personally as well. We're kind of unique in the business that we provide a lot of parts. So we supply amplifiers and detectors and scanners and whatever you might need to build your own systems. And we do that as a way of encouraging independent developers, whether in academia or in industry, to build their own system and to build their own microscopes, because a lot of the time the main barrier is electronics. Right. About today, we will focus on TEM and EBIC, and for us that falls within electrical analysis. And I will speak more details. Why do I use those words and what do I mean by them? And we are based in quite a different types of range of microscope for this, and it very much depends on the application which microscope is best suited. But historically, we dealt with these kind of techniques primarily in ASEM. And I would say that's probably the most established community, and Protochips has made a great advancements in TEM to make all these techniques possible through their sample holder. We do quite a few different kinds of techniques, from measuring resistance, imaging fields, measuring combination of defects, and so on. So quite a wide range of techniques for SEM. Sometimes it makes sense to use this in scanning confocal microscopy, where you want to have high yield and less sample preparations. But today we're going to talk about doing it at TEM, where the main drivers, I would say, are resolution. You can see much more finer details that you could see in the SEM, and that is the advantage of the TEM, and it matters a lot as the device gets smaller or research on nano devices is taking off. The kind of two techniques that I'll be highlighting through, one is EBIC, electron beam induced current, and the other one is secondary electron beam induced current, which is a term that the guys at UCLA have come up with. There will be Dr. Hubbard and Professor Regan from California. And I will, as we go through data and images, I will highlight both of these types of signals.
Thank you, Greg. So now let's get started. And I would like to start with a fundamental question. Just why in situ? Why bother sending a stimuli inside your TEM column? And to answer that, I would like to take the example of the crystallization of water. When you perform a static observation, you can easily see that depending on the temperature at which you trigger the crystallization, you have different structure. But it's only by observing the live mechanism in situ, by monitoring the dynamics of this event, that one can understand it better. And it gives you access to a larger varieties of solution and results, because by understanding the event, you actually gain control over it. And to me, this is what in situ is about in the TEM. At the nanoscale, getting to understand dynamic events allows you to control them better and unlock new possibilities. And this applies to a very wide range of application, in situ in general and in situ electron characterization more specifically for today, from semiconductors to microelectronic, the development of new devices like resistive memories, alloys and metallurgy, of course ceramics, ferroelectrics and power electrics that's been widely studied in situ, and there are many more. Many of those fields have had important breakthroughs over the recent years with the help of in situ transmission electron microscopy. And for today, we're here to talk about scanning transmission electron microscopy combined with electron beam induced current. But first, while Greg is later during the second part of this presentation going to tell you more about the electron beam induced current part of that combination, I would like to start with the in situ TEM part and basically address and describe what you would need to do any sort of in situ work inside the TEM column. To do such thing, you would need a fusion select system in this case. The fusion select is initially a single tilt heating holder, which is designed in a modular manner so that you can, on top of its basic function, add a double tilt functionality, a electrical characterization capabilities that is going to be of interest to us today, or electrothermal to combine simultaneously heating and electrical biasing. And the idea behind that is that you can select one or several packages depending on the need of your projects and the funding available at a given time, knowing that as your research evolves and as the opportunities evolve, you can always unlock the full capabilities of the Fusion Select system whenever you desire. The Fusion Select system is powered by the Exxon Machine Vision software, the latest developments in Protochips, and this is a software that allows complete synchronization in 3D space of the region of interest of your sample during an observation, and also simultaneously allow complete synchronization of data and information flowing between the different elements of your system, between your TEM column, the different cameras and detectors, and your in situ holder. And this allows to greatly improve the quality of data, the ease at which you access the data, and makes processing much more powerful. But mainly, it allows you to access to result and information that could not have been obtained otherwise. So the Fusion Select has 3 different functions. And so for those not familiar with in situ TEM, compared to regular TEM, during a regular classical TEM analysis, you would place your sample on a copper grid. The copper grid would be your support for the sample that is placed on the holder. In the case of in situ system, we place the sample on a MEMS chip, a silicon MEMS chip. But this MEMS chip, in addition to being the support for the sample, actually defines the stimuli that you're going to apply during your in situ experiment. So you have electrical characterization MEMS chip, you have a heating MEMS chip, and electrothermal MEMS chip. And no matter the different brands of microscope that you have, and no matter the packages that you've selected, there is a single format for those chips. So if you have collaborators or if you have several brands of microscope, you can use the same sample on the same chip and move it around and make correlation much more efficiently between your different instruments. So what does the chip itself looks like? So in the case of electrical chip, it's a 300 micron thick wafer, and the wafer has been etched in order to produce a suspended electron transparent silicon nitride membrane on the surface. And this electron transparent area is going to be your observation area, and on top of it is running different electrodes, and there are many many layouts available, and you have different materials available depending on the experiment that you want to perform, the kind of stimulation that you want to apply, the form and shape of your sample, but also the sample preparation method that you would like to use. And basically, there is always a design that is going to facilitate your entire characterization process. And the same is true for the heating chip. So the difference is it's still a 300 micron thick silicon wafer, but the heating element, what is allowing heating of the sample, is actually a 120 nanometer thick silicon carbide membrane. And you can select then on top of this basic layout either to add, you can use just the silicon carbide heater, but you can, on top of it, add a 40 nanometer continuous silicon nitride film. For example, if you would like to support nanoparticle or deposit thin films, or you can place instead a 18 nanometer holy carbon grid, identical to those used in the C-flat device, for those who know them, for extremely low contrast and very small particle, for example. So what does the full system look like? If we take the example of those white nanoparticles, they're placed at the center of the heater in black here on this chip, and then you have electrodes running on the chip in order to reach contact pads. Those contact pads in yellow are connected with the probe as the chip is loaded, and the flex tracks brings the signal to the back of the holder. And this is where selecting the chip is going to select the function of your experiment. So now you can insert the holder inside the column, and you're ready for observation. And it's important to note that Protochips system and Protochips holder are designed to fit even very narrow pole pieces, even narrow gap in pole pieces, while leaving you some room to perform tilting as well, which provides additional flexibility when working on such equipment. Once in the TEM, you can perform tilting in both directions with a friction-free design that ensures that the heating or the electrical stimulation that you send is crystal clear and not disturbed by the tilting mechanism. And the full idea also behind that design is that you can access all of the tools that you have in your microscope, from the tilting to the EDS detectors as shown here, EELS, TPC. You don't have to limit yourself in any way when doing an in situ TEM experiment. You can still benefit from the full capabilities of your TEM. So what does a final result look like? In this example, this is from Mark Willinger at ETH in Zurich. It's a core shell silver nickel phosphate particle. And we've been able to observe extremely rapidly during the first test the phase change happening at atomic resolution during a live heating stimulation. So during an active change of temperature, the region of interest was perfectly maintained around the particle. The field of view was perfectly maintained around the particle, and we could witness the entire procedure at atomic resolution. And this is the kind of result which is unprecedented and is impossible without the combination of the Fusion Select system empowered by Axon. So now let's get to the core of the topic, and electrical characterization and all of the different methods associated with it. Well, for many years, actually, there was a bottleneck in that field, which was sample preparation. And this was due to several factors. One of them being that the MEMS chip, the sample support, was not specifically designed for devices and lamella-shaped samples. It was more designed for nanoparticle and nanomaterials in general that needed support. And secondly, because by the nature of the sample preparation process, there are many artifacts listed here that were well known because it's a method used for decades, but because of the in situ aspect of the experiment, those known artifacts brought new challenges, such as short circuit and leakage path, preventing accurate characterization of your device, the precise circuit edit, which is required because when you extract a specific device from a complex element, you need to reconnect it and you need to perform small modification at a very small scale. And because of regular TEM imaging, you still need to have a very thin, very clean and high quality sample. And most importantly, the entire process needs to be reliable and reproducible so that you can perform the experiment many times and obtain relevant information. And this is why the FIB optimized chip was developed. And this is actually a chip that was designed, that was developed as a first prototype between 2016 and 2018, when I was myself a PhD student at CEA in Grenoble. As a PhD student, I contacted Protochips because I was using a fusion holder at the time. And we actually collaborated together in order to produce and test the first prototype of this FIB optimized chip. And it's only thanks to that chip that I got my PhD results. So the way this chip works is actually extremely similar to the way a regular copper grid for regular TEM observation is being used. And this is the power of it, because the entire method is extremely identical. The entire sample preparation method is very identical to regular preparation on regular TEM, making this procedure very easy to learn and very easy to implement. Secondly, by the nature of its design, it prevents the formation of any short circuit and leakage path around the sample that would prevent you from performing an accurate characterization. And also, by its design, very similar to a copper grid, you can reach the same quality of sample in terms of thinning and cleaning as a regular user of FIB and TEM could perform. So as shown on the image on the top, it's a regular lift out of a brick of material. And the only difference between this preparation and a regular preparation for classical TEM is that instead of attaching the sample on one side, you attach it on two sides, on the two electrodes, in order to have your two terminal and have a closed electrical circuit. Beside that, the entire thing is very, very similar to regular preparation. And this method was used recently during a very successful collaboration that was done between Intel in Israel and Protochips. So they contacted us because they wanted to observe a very specific via. In a very complex stacking, they wanted to observe a very specific via. So a via is this metal connection that is going to link different layers, different level of a very large stacking, a very complex device. And as a matter of fact, sometimes those via fails, and they wanted to observe how does such a structure fails and disconnect when you apply a very high current through it. So we applied the method that we just described, and we were very successful and we've been able to observe the in situ failure event, the entire dynamic of this event. We've been recording the movie of that, how a void, so a hole inside the via, was nucleating and growing and changing its structure and its morphology, how thanks to EDS analysis, different chemical elements were migrating and modifying the property of the structure, how the polarity that you were applying to this wire in order to run a higher current, how this polarity was changing the behavior of the failing mechanism, and link all of those structural chemical information to electrical property of the wire and see how it was disconnecting. And by understanding by monitoring this mechanism, by recording it, we've been able to understand it better, and it's a key part in order to produce, better device, next generation of device, and improve the entire procedure. So before I give the stage to Greg, that is going to tell you about how to use this fusion select system, how to use in situ TEM together with electron beam induced current analysis. I would like to summarize what the system looked like inside the TEM. So you start with an electron transparent sample, which is connected to two terminals, shown in green and red here. When you zoom out, you see an overview of the FIB optimized chip, and the contact pad of the sample, the two terminals, they run on metal tracks on the edge of the FIB optimized chip and reach those contact pads. This FIB optimized chip is 4 millimeter inside, so this is what you would manipulate with your tweezers in order to load on the tip of the fusion select holder, like this. And the electrodes that you see here are connected to the probes and to those cables running to the back of the holder. So you see a wider view of the TM holder with the tip, which has the sample loaded on it. And this is where you insert in the microscope in order to be ready for imaging. So now your sample is inside, ready to be imaged, and at the back of the holder, you have up to 6 terminals, all triax connectors that you can plug to the instrument of your choice, either the standard Fusion Select package to perform in situ TM experiments, or as Greg is going to tell you more about, an electron beam induced current setup. So thank you, and I pass now the stage to Greg.
Thank you, Rémy. First, let's switch the presentation. It may happen that you lose the slides connection, and you don't see my slides on screen. If that happens, then just please sign out and back in. It should be very quick. And I will spend a minute or so on this slide so you have time to do it. So now you should have my slides on screen. So Rémy has talked about two things that Protochip has done a great job bringing together: electrical characterization, which kind of comes more from device engineering, electrical electronic engineering, and electron microscopy, and kind of comes more from material science. And historically, this has been quite hard to do. And I remember when I first tried to do it 20 years ago, I had to build my own holder, and that's a lot of time and a lot of effort. And that barrier is gone. And I would say the talk, for me, the slide that we're show today primarily talk about removing barriers and making work easy. But definitely there was a big barrier in the past, which is no longer there anymore. So what I'm going to talk about, electrical analysis, is now very easy, what used to be very hard. Another part of doing electrical analysis, combining all this together, has been sample preparation. Tripod polishing, it's great, but it's hard and it's time consuming, and it doesn't have very good yield. And with a FIB now, all this is becoming routine. It's very, very, very straightforward indeed to do all these techniques that we're going to talk about today. So that's two barriers we removed. And what I want to talk first about is another barrier of understanding of what is possible. There have been publications out maybe since the 80s, early 90s about doing this kind of analysis inside TM, but it was always very, very hard, and therefore a very small community that was determined enough really to spend the 1 or 2 years to get to the equipment and then get you to the experiment. But why would people want to do this? Well, electrical analysis is a bridge between electrical characterization and electron microscopy. And it's a bridge for device engineers. They want to be able to bring their knowledge into microscopy, and for microscopy, they need to kind of bridge into device curves and understand how everything comes together. And it's an important bridge that brings everything together. Without it, it's very hard to make this transition between device language and what a device does and what it is with a very high resolution that a microscope can bring. So what do we mean by electric characterization? We mean the experimental methods that you use to probe and measure device properties. So you know you have a diode, you know you have a transistors, you know what kind of diode, what kind of transistors, and you know what kind of IV curves you want to run on it. And you use an equipment which would be, maybe this is quite a standard equipment for a lot of labs, a semiconductor device analyzer. And you tell this device, this equipment, what device you have and what curves you want to use, and it will run it and it will extract parameters, and it will tell you what is the turn-on voltage, what is the breakdown voltage, what is the leakage current, and all these parameters you need to know about devices. So they can feed into production or feed into research or feed into reliability, failure analysis, whatever it might be. So this is very established, very straightforward. On the TEM, the other hand, you move into a very different kind of world, very different kind of equipment. And I don't want to wish any particular manufacturer, but you have very high resolution and you can see the interfaces. And down to atomic resolution, you can see the interfaces in your device and you can see the composition and structure and defects. And that is wonderful. You have a very powerful insight on what a device is. So for diode, you can see the connections, you can see the interfaces. For transistors, you can see the oxides, you can see how uniform, how you can measure the thickness, you can see the poly, you can see the metals and all this information. But what you really want to bridge between this world of high resolution to this world of device curves is you want to know where are the fields? You want to know what electrons and holes do in your device. How do they behave? And that is the world that electrical analysis is trying to uncover. Not only to see the structure, to measure the composition, but also to see the fields, to understand diffusion, drift. You see the shape of everything with high resolution inside a microscope. So how does this work? We're taking advantage of electrons coming from the primary beam, interacting with the device and losing energy into it. And when they lose energy through this inelastic loss, they excite electrons from the valence band to the conduction band. And they create an electron-hole pair. This happens every time you have a band gap, whether it's semiconductor, ceramic, whichever material it may be. And normally they recombine, they attract it together, they recombine, and they result in heat or light and whatever other else things may be. But in the presence of a field, they separate. They each go in different direction. And therefore, we have a chance to pick up a current. And this current is called an induced current because we have induced the electron-hole pairs and we collect in some of them. And that's the signal we'll be using. Normally it's thrown away. Normally people just want to look at structure or composition or whatever. But in this case, we will use that to build a better understanding of the device. Other things happen at the same time as always. We have, of course, X-rays. We also have secondary electrons. And this was the other type of signal that I would like to focus on today. As the electrons, primary electrons interact with the sample, they excite electrons with sufficient energy that some of them will leave the sample. And when the secondary electrons leave the sample, we need to put those electrons back. And they will be drawn from our circuitry back into the sample. And a term that has more recently been used to describe this is secondary electron beam induced current, which is quite a long acronym. Other things happen at the same time. So the transmitted electrons go through the field, and they are slightly deviated. So you could pick that as well with differential phase contrast, for example. And a very well-established technique to look at fields, whether electric or magnetic like VPC, but older and really sophisticated, I should say, and established is electron holography. But electron holography requires a lot of interpretation. You get a diffraction, you get an interference on the camera, and you have to process that interference in order to extract the phase and the amplitude. What we're going to talk about today is very simple. In this regard, we're simply just extracting this current and we're going to display it. What we can also do, we can apply a bias, and therefore we can make this depletion width wider or narrower, and therefore we can see that in our imaging. So we can play with the device, we can interact with it, and see how the fields react to the operation. So you can look at fields in the same conditions and its normal operation. So coming back to the sort of devices that Rémy was showing you, sample preparation, we have a p-n junction. I would say this is more of like a proof of principle. This is just going through an experiment that goes through the motion and shows you what's possible. We know this is a diode. The point is to illustrate what it's possible to do. We have a diode, and that the dotted line shows us where the diode is because we know the depth from the surface. And lamella is extracted and finished on a grid, one of the Protochips carriers. And we have two connections, left and right, one to the top and one to the bottom. And we're going to look in cross-section. And we have finished this lamella at different thicknesses as a way of illustrating what happens if you have samples at different thicknesses. And we're going from 350 nanometers to 390, 500, all the way to 1 micron. And now if we just switch to this induced current, and all we're doing is that we're measuring the current at every beam position, and we plot this as an image. So we do this in the same way you would do with HADF or Brightfield or EDS or any other kind of detectors. So there's no analysis. You just look at the image as it arrives from the system. We see this secondary electron effect. So, and because this is stronger, the thicker the material, and the higher the density. So in this protection layer and connections, we see it quite strongly because it's thicker and higher density. And in addition to it, we also see a line where the junction is. And this is where the electric field is. So we have a direct image of the field. And we can see that the intensity of this line depends on the thickness. And that makes sense. The thicker the device, the sample, the more energy we lose, the more electron hole pairs we induce, therefore the higher the current that we pick up. And if we take a zoom in, we can see the field, and we can see this decaying edge. And these are the electrons that are diffusing, walking randomly around the sample and then reaching the field and then being driven across drift. A unique feature of EBIC, many other types of signals in the TEM, is that we measure the beam current, and we measure the induced current at every point in the image. So our image is quantified, and we know the relationship between gray level in the image and current. So at every point, we can say what current we measured. And that's important for quantification. And this is work done by a group in Grenoble, Cialetti. They do a lot of service work, so they do a lot of work on devices as well. And this is very careful work by Aidan Rooney, and I encourage you to read this paper that just came out the other week. And he's had a close look at quantification, which is a traditional topic in EBIC analysis. If you take a line across this profile at different thicknesses and plot it in semi-log, you can see this diffuse decay, and that's related to the diffusion of minority carriers. So we can measure from this the diffusion length of minority carriers. In this case, we know that the material is quite high quality, so the diffusion length is quite long, it's more than a micron, but we can see that it's limited by the thickness of the lamella to much smaller diffusion length. In other words, there isn't space for the minority carriers, whether electrons or holes, to move around. That's in effect induced by a lamella, and this is one reason why we get higher resolution in EBIC in the TEM as we were in the SEM. So another example, again from the same group in Cialetti in France. This is a nanowire. It's a silicon germanium nanowire. And this is work that they've not published just yet. So I'm not showing you all this data. They will show more high resolution and more analysis in when they come out, but I don't want to spoil it for them. But in principle, it's quite straightforward. It's a silicon nitride membrane. It has two aluminum pads, contact pads. The silicon germanium nanowires is put across, and it's heat treated. And by heat treating, aluminum is diffusing into the nanowire, and only in the middle we have left silicon germanium, and we can see the aluminum diffusion from both sides. And they have done great work looking at the interfaces with high resolution TEM and see what those interfaces are. And for example, they see that they're not the same. They're different interfaces on both sides. And that's great. That's the microscopy side. You can do a lot of sort of high resolution work on it. On the other side, you have the device characterization. So we can do an IV curve, and this is done with our equipment. And you see this IV. And the question is what do you see? What does it mean? What are you looking at? Are you looking at like a liquid diode? Are you looking at are there some fields there? It's very hard to say by just looking at this data. And that's the power of EBIC. At the same time as you manage to image HADF, you can also image EBIC. And in the EBIC, we immediately get two peaks, two spots. And because we know the relationship with the current, we know that one of them is positive and one of them is negative. So one is bright and one is dark. And they are colored here in pseudo-color just to be able to make it easier to look. And because we see these two regions, we know we have two fields. That's what EBIC does. It shows us where the fields are. It also shows us the shape of the field. So we see that the field is inside, and the silicon germanium nanowire, of course, cannot be inside the aluminium. And we also know it's opposite. We're collecting holes from one, electrons from one, so we know they're back to back. So immediately we have a little circuit that we can model all our experiment to. We can say we have two interfaces, both have an electric field, and we can add some resistors to account for the motion of current through the nanowire or around it, through the surface of the nanowire, or if you like, even through the silicon nitride, if you think that would be a case. So we can immediately go back to the IV curve, model all these two diode circuit, and we can start to extract some device parameters that otherwise we would not have enough confidence to say they are meaningful. What is typical for EBIC is that you can do very detailed Monte Carlo simulations. We know from the high resolution work what is the size of the nanotube. We know its composition, so we can have a 3D model of it on top of the silicon nitride, and then we can model the electron beam going through, and we can see the interaction volume, the lateral displacement, and so on. And it's a way of increasing confidence in the results that you see. The numbers match the experiment and the simulation. That makes for a much stronger publication as well. And in situ, so we can play, we can work with this device inside, and we can see how it reacts to bias. So we generate a small voltage, and I'm showing here only between half a volt plus and negative, but more is possible. But at a null bias, we see that the self-biasing of the diode. So it's a built-in bias. If we apply only half a volt, we see that one of the fields it's increasing in width, so we increase the depletion width, and the other one is disappearing. So one is in reverse bias, and the other one is in forward bias because they're back to back. And we see this repeating as we go to the other voltage. And Aidan has done very careful work where you apply different levels of bias, and you can measure the amount of current you record and the width and so on, and you can extract even more information about the nanowire and the junctions that you have formed. And then a third example, and this is illustrating another strength of doing EBIC in the TEM, is that you can do other kinds of analytical techniques at the same time. So before we looked at structure, now we're looking at composition. So from the same sample, on the same location, we're recording EDX and EBIC. And EDX is giving us the composition, and this is a heterojunction solar cell. And we have a silicon-to-silicon heterojunction somewhere in this region. And we can pick up with EDX the composition, and we can see the layers. And the question was, where is the junction? Do we have a junction? Where is it? How does it look like? And it's very straightforward. You just do one image, and you have a location of the field, and you can start to do more analysis from it. As I was talking before, we always get this secondary electron effect as well. So we have some secondary electrons leaving the sample as a function of thickness, as a function of composition, and it's giving us a small background. And on top of this background, we have the stronger EBIC signal. And some level of training and analysis is needed, interpretation is needed in order to say which is which. And you can take a line profile, and you can see where the peak of the EBIC is compared, for example, with the HADF or the oxygen on EDX. And you can say how lower the field is compared with the interface into the silicon. So these are a few quick examples to show you what is the power of this approach and why electrical analysis it's building a bridge between electrical characterization and structural characterization or chemical analysis. Another section now, we will look a little bit over the equipment. What equipment do we need? Well, we are measuring very small currents. So we're measuring the fraction of the beam current for these SE electrons and maybe around a bit more than the beam current for EBIC. And we want to do that very fast. So we have dedicated electronics for this, and everything is designed bespoke to fit the needs of this kind of signals. So that means that we have two-stage amplification, which is quite sophisticated, And we also have to deal with safety aspects of switching signals from one route through another. So we have routing, and there's a lot of optimization to do in order to match the signal to the imaging, so we can build an image that is not saturated or not compromised in any way. And of course, we also have to have the electronics that deal with the biasing, whether it's the voltage source that you need in order to interact with the device, or also current source that we can compensate whatever leakage current or forward current may come up because of this voltage bias. Another unit that completes the system is a scanner. It's generation 6, and this is the most powerful we've ever made of a scanning system, and this is the one that will connect to the external scanner of the interface in the same way that EDS or EOS and so other TEM techniques do. And it will generate a scan, it will tell the beam where to be and where to go, and this is the one that it's also digitizing all the signals, and we're digitizing at quite high bit dynamic range, 16 bits, in order to retain the best signal as we can for electrical analysis. It's a powerful unit. It's a bit more powerful than it needs to be, I would say, for this. It's also able to do raster and vector, not only raster scanning the images that I've shown, but it can sort of vector scanning. So if you want to do sparse sampling or whatever other kind of scanning, it's also possible to do with this. This is a generic unit for us that we're just using for electrical analysis. In terms of installation, how does all this come together? Well, we have, in the first instance, a preamplifier that goes close to the biasing holder. We need to do that in order to minimize the amount of noise that we pick up on cables and connectors. And these are the minimum two connections that we need to the biasing holder. And here we deal with a preamplification, and also with a second, which is a high-speed preamplification that we do for imaging, and then another amplification that we do to measure the beam current, which is slower. And then that goes to the amplifier unit that deals with the remaining of the amplification and time filtering and so on. And then that goes to the imaging unit that brings together the EA signal with other signals from the microscope into a control PC, which is then on the network to move your data or connect to the TEM. The software aims to be quite lightweight, so not to overwhelm you with too many buttons and options. But there's a lot of power, and everything can be configured. As you go deeper, you get more and more options. But it's an imaging software, and it kind of follows the concepts from microscopy. So we have a lot of space for images, and then we have different scan profiles, so you can move between navigation to adjusting things to final acquisition, slow acquisition, and all the controls for brightness, contrast, and biasing, and other controls you might need for the experiment. It's on the right panel. But there are a few unique features that are very important for this kind of analysis, and one of them is to be able to acquire signals simultaneously. And we really mean simultaneously, because we don't want images to drift and to be a slightly different magnification. So we really mean we move the beam to one position, we digitize all the signals we want to digitize, and then we move to the next pixel position. In that way, we guarantee that when you mix these images, they will overlap in the same region. So that's when you mix them, we do that to see where the field is, and we tend to colorize in red or whichever other color and overlay through HADF, for example. Then we can say the field is here, and we can say reliably measure things, how deeper it is from what interface and so on. Another thing that is bespoke to this kind of work is the ability to mix microscopy with characterization, device characterization. So the software comes with an IV curve tool. So you can specify a voltage range, and you can run an automated IV curve, so you can see how the current is changing for different voltages. So you would do this for device characterizations to see what have you connected to and make sure everything is live. You would also use this as a way of managing for beam damage. So for example, for diode, which this IV is, for beam damage, you will start to see a higher leakage curve over time. So this is also a tool that you need to ensure that the data you record is correct and the device is not changing over time in the microscope. And then finally, come to offline software. We want all this information about what biasing you applied and what imaging conditions you had, and it's saved it together in a TIFF file with the image. So we provide an offline tool that you can view all this information. You can see all the different signals you recorded at the same time, and all the conditions that you use to record that. And we like standards, so we use TIFF, we use JPEG, we use standard metadata and XMP from Adobe and so on. And of course, we know everything about the amplification. So we know the relationship between pixel value and current. So this we display here as well, and you can go for every pixels and you can read the value. You can export a whole image if you want to do other analysis of your own. So this is all meant to be straightforward and take advantage of the quantification of the technique. In terms of knowledge, first I must acknowledge Protochips for organizing the webinar. I'm very grateful for that. And also I need to acknowledge Dr. David Cooper at CLETI. He is the one that brought all this together in terms of equipment. So I've been chasing EBIC and TEM for on and off for about 20 years, but he's the one that said, let's do it. We'll put a microscope, make the microscope available. We'll bring the Protochips and you together, and we were able to acquire all this data that you have seen. And I asked him to send me a picture, and he did, and said, please make it small. And I said, no, it's a good picture, make it large. So here he is, just this week up the mountains in France. That is all for me. I will give now back to Jen.
Hey, thanks, Greg. Thank you both. We did get a handful of questions that came in. And so I'll try to assign them to you, but feel free to pass them off to each other just for simplicity's sake. If I assign it to somebody first, and then if you're not the best one to answer, feel free to pass it off. We had a few sample prep questions actually come in. Rémy, I'm going to send them to your way, and feel free to give to Greg if you would like. But the first one was, what exactly are the two center contacts used for? In the example images, only the outer 4 or 2 were used.
Yes, that's very true. So the chip that we showed in this presentation that we used in the collaboration with Intel was a chip with 4 contacts from the previous generation of Fusion Holder. But it's because we had no use for the central 2 contact, we wanted to do 4-point probe measurement on a 2-terminal device. And we did, but it depends on the chip. You have, for example, an electrothermal chip that use all 4 contacts. So we only need 2 for accurate heating, thanks to the properties of our heater technology. And then you have 4 available for biasing. So you can have a very accurate heating simultaneously with very accurate electrical characterization. So it really depends on the chip that you want to use. We only needed 4 in this example.
I can expand a little bit if you wish.
Mm-hmm.
So for device characterization, 2 contacts, you can start to do work for devices that have 2 terminals. 4, it's better if you want to do remote sensing. So you want to take into account resistance of connections as you go through the cables and through the holders and through the chip and all the rest. For electrical analysis work, for EBIC 2 are enough. And because it's a current technique, resistances don't matter very much. 2 is plenty. If you want to then map resistance and you want to use other electrical analysis technique, then it's useful to have more. Then in terms of what kind of device you have, or transistors, you might wish to have 3. For memory cells, you might wish to have 6. So it kind of fits into the device that you want to have for analysis.
Great, thank you. Rémy, I'm going to throw this one to you first as well, and then Greg, of course, feel free to add on. In one of the slides, low energy argon thinning was mentioned. Have you already tried this? If so, which instrument did you use, and did you experience any challenges?
So yes, the FIB optimized chip in particular is perfectly suited for low energy broadbeam milling. I know some manufacturers that have provided stages in order to have one of those chips loaded and inserted and be able to perform those broad ion beam milling. I've never done it myself. I think I've seen it. I did use it, I think, on a nanomill. I saw it used on a nanomill, but I've never done it myself.
Okay. And for the sample prep, one more sample prep. Let's see, how did the team at Grenoble make the contacts onto the chip, and is the resistance of the platinum contacts a problem?
So the contacting is done when doing a FIB preparation either with tungsten deposited by ion beam or platinum deposited by ion beam. Both material, after studying them by 4-point probe measurement, have demonstrated very high conductivity, a conductivity which is about 1 order of magnitude below pure crystalline equivalent in general. Although it depends on the FIB and it depends on the lifetime of the precursor that you're using. There is one thing though, is the contact of FIB deposited material between FIB deposited material and another material is not perfectly ohmic. And it's been well documented, it's well studied, so there is a bit of resistance there at the interface. But as Greg said, on a technique based on current like this, it's not a problem. And in any case, it's well documented, so it's easy to adjust for it. And it's nothing big, it's a few hundreds of ohm, maybe a kilo in some cases. I've never seen more than that.
Let me complete the answer. So if you do device characterization and you do local sensing, then of course you will see some resistance in series with your device, and that's something you should take account into your modeling, and it's something you can also measure experimentally if you wish. When it comes to electrical analysis, if you do a current-based technique like EBIC, then it doesn't really matter. The current wants and needs to come out of the device, whether it comes through 1 ohms or 10 ohms or 100 ohms, it really doesn't make a difference. If we use a different kind of technique, so it's not something that I talked about today, like resistive contrast imaging. So this is a technique that we use to map resistance. Then we can map the resistance along these connections. So it is there, and we can map it, and you can see it. But it's not playing a significant role. It's not stopping for any experimental work.
Great. So next question would be, the equipment from Point Electronic, is it standalone? What equipment in totality do we need to perform the kind of electrical measurements you have shown today? So do you want to just summarize everything again on what you would need to perform the examples that you showed, Greg?
Sure. It's a turn-on system, so we supply everything that is needed for it, and we come and train and make sure that everyone knows how to use it. So the installation would take perhaps a couple of days and the training another couple of days. You need the biasing holder, that's an important part, and that comes from Protochips. And then you need the 2 units that I've shown, plus all the cables and so on. Cables that connect between the holder and the different bits of the electronics, and also from the electronics to the microscope. But it's a self-contained system. We can supply it with or without a PC. And because this connects over USB to the hardware, it's quite straightforward to use really any kind of PC. So it's, I would say, very straightforward. Of course, you also need to take into account that you need chip carriers, and that's what Rémy was talking about today. And you need to be in good control of FIB preparation. And I think some training can come from either of us if you're new to this area, how to prepare chips for this kind of technique.
That's perfectly right. So we do provide application training, either depending during the installation or later on. We can provide application training, and we provide sample prep support remotely in any case to all of our users.
Yes, and of course support. Yes, of course.
And we have detailed step-by-step guide with the entire procedure, all of the images of every step of the way, all of the current and values for every beam, the precursor use, tips and tricks. We have a very detailed guide that you can use to train new people joining your lab, or you can use during the first time you make the experiment. But again, in the case, all of the results that were shown here, the sample preparation is very easy.
Because we design our electronics in a way that it's very disconnected from the computer, we and we use USB, for example, for it. It means that we give us a lot of freedom, and we encourage our users to put their control computer on the network, and then give us remote access as much as possible, so we can see what you have on screen, so we can guide you remotely. And this is support that I think is very welcome for somebody that's new in the field, and this is something that we're very accustomed to.
Great, thank you. I got a couple more here, and then we can wrap up. Do either of you have any comments on to what measure was carbon contamination during STEM observation noticed, and would it influence the electrical analysis results?
Go ahead, Greg.
Yes, it's of course depends on all the condition of the microscopes and how clean case is, and of course it's important to do some plasma cleaning to prevent from that to happen. But in any case, you always need to when you do the modeling and you say, okay, I know I have some diodes and I'm going to model some added resistors. One of those resistors should account for contamination or for any surface damage layer that we made during preparation. And this would be something that would be a resistor in parallel to your diode for the field or whatever. And if we talk about contamination building up in the microscope, you would see this resistance changing over time. So let's say becoming smaller. And you should see that in the IV. And that's one reason why we do supply an IV tool with a system. So you can run periodic IVs, or where you feel that it's necessary to see if the IV has changed. And if it has changed, it would be either because of contamination or because of beam damage. But it's on these samples, they have eventually died in the microscope, and I think they were, a very big thirst for data. Let's take a lot of biases and let's record images for each bias and see how everything holds on over time. And there was a case of the nano, but I believe that the simple diode example, the one that I shown first, was very resilient. But yes, it's something that you need to be aware of and need to be knowledgeable. It's not though a showstopper. It's just
from experience, the carbon contamination, as long as you perform a clean sample preparation and you perform a plasma cleaning before you insert it in the microscope, and provided the quality of the vacuum in the microscope is good, is very similar to a standard experiment. And I've never had issues with that in any way.
And then there, as you become more advanced, you start to learn about new tricks and things you can do. Of course, you can power your device because it's all connected, and when you power it, it self-heats, and when it self-heats, it self-clean. So it's but you have to know what devices you're doing, what is going through.
Exactly.
Okay, so we've made it through these questions. I believe that I can see we got all of these answered. So yeah, I think it would be, unless either of you have anything additional you'd want to add, I think we would be good to wrap up and thank our audience. Is there anything you two want to add?
All good.
All good.
Okay, great. Well, thank you everybody for joining us today. We really enjoyed having you here, and I hope that you found this really interesting and inspiring. And if for some reason we missed a question, we'll ensure to reach out to you with a response. And otherwise, we hope to talk to you soon, and have a great rest of your day. Thank you.
Thank you.
Thank you very much. Bye.